Welcome to our discussion on accelerated aging in people living with human immunodeficiency virus. We'll explore the role of mitochondrial dysfunction in this process, as outlined by me, Dr. Martin L. Ganoni, in the Norton Healthcare Medical Journal. Well, it is not me, it's my avatar, but we look identical, although I would like to have this voice, Jesus. Of note, the journal does not exist anymore, so if you want a copy of my manuscript, I will upload it for free access. Antiretroviral therapy has revolutionized human immunodeficiency virus treatment, transforming it into a chronic condition. However, people living with human immunodeficiency virus face a paradox. They develop age-related diseases like cardiovascular and metabolic disorders much earlier than their human immunodeficiency virus negative peers. This phenomenon, known as inflammaging, involves chronic inflammation accelerating organ dysfunction despite effective viral suppression. I hypothesize that human immunodeficiency virus-associated mitochondrial dysfunction, HIVAMD, I created the term, copyrights reserved, is the primary driver of accelerated aging in people living with human immunodeficiency virus. It arises from human immunodeficiency virus's disruption of mitochondrial processes, chronic inflammation impairing cellular functions, and antiretroviral therapy side effects inhibiting mitochondrial DNA polymerase gamma. This dysfunction is a central, targetable mechanism in aging. Understanding human immunodeficiency virus-associated mitochondrial dysfunction starts with normal mitochondrial bioenergetics. Mitochondria generate adenosine triphosphate via oxidative phosphorylation in the inner mitochondrial membrane. Healthy function involves a seamless electron flow through the electron transport chain, generating a proton gradient for adenosine triphosphate synthesis with minimal reactive oxygen species production, supported by adequate antioxidant levels. Here you can see the normal functioning of mitochondria with matching energy supply and demand. The leaky hose model illustrates mitochondrial dysfunction. In a normal state, electron supply and adenosine triphosphate demand are balanced, ensuring efficient adenosine triphosphate production. In an overloaded state, excess nutrients cause electron leakage, disrupting the proton gradient and increasing reactive oxygen species, leading to mitochondrial damage. Mitochondria produce uncoupling proteins to reduce oxidative stress, but this decreases adenosine triphosphate efficiency. Here on this graphic, you can see the mitochondrial chain as a hose. Here you can see overload of the mitochondria between supply and demand with oxidative stress as a result, and ineffective ATP production. In people living with human immunodeficiency virus, PLWH, aging hallmarks occur at accelerated rates. Mitochondrial dysfunction is central, with nicotinamide adenine dinucleotide, NAD+, levels declining up to 50% between ages 40 and 60. This decline impacts adenosine triphosphate, ATP production, sirtuin activation, and mitochondrial integrity, highlighting the compounded challenges faced by PLWH compared to human immunodeficiency virus negative individuals. Mitochondrial dysfunction drives age-associated cellular decline in people living with HIV, leading to frailty, cognitive decline, and cardiorespiratory issues. Decreased muscle mitochondrial efficiency causes early frailty, while reduced oxidative phosphorylation capacity limits exercise tolerance. Impaired adenosine triphosphate production contributes to chronic fatigue and metabolic syndrome, exacerbating insulin resistance and cardiovascular risk. Human immunodeficiency virus disrupts mitochondrial DNA repair by impairing proteins like ataxia-telangiectasia mutated and P53, leading to accumulated mutations and increased reactive oxygen species. Senescent immune cells release senescence-associated secretory phenotype, spreading mitochondrial dysfunction. People living with human immunodeficiency virus exhibit increased senescent T-cell markers, resembling those of older human immunodeficiency virus negative individuals, with elevated tumor necrosis factor alpha and decreased naive T cells. Human immunodeficiency virus proteins, including GP120, VPR, TAT, and NEF, sabotage mitochondrial function. GP120 disrupts the electron transport chain and triggers apoptosis. VPR degrades mitofusin 2, impairing mitochondrial fusion. TAT accelerates senescence by downregulating BCL2. NEF inhibits autophagy, allowing damaged mitochondria to accumulate, promoting human immunodeficiency virus persistence. Modern antiretroviral therapy regimens, while safer, still impact mitochondrial function. Nucleoside reverse transcriptase inhibitors inhibit DNA polymerase gamma, reducing mitochondrial DNA copies and increasing oxidative stress. Non-nucleoside reverse transcriptase inhibitors and protease inhibitors promote apoptosis and oxidative stress, while integrase strand transfer inhibitors cause a metabolic switch and respiratory chain deficiency. Each class affects mitochondrial health differently, highlighting ongoing challenges in antiretroviral therapy management. Cluster of differentiation 38. Overactivation in people living with human immunodeficiency virus leads to nicotinamide adenine dinucleotide depletion, impairing adenosine triphosphate production and suppressing sirtuins. This triggers a pro-inflammatory cascade, causing mitochondrial damage. The metabolic switch to glycolysis destabilizes mitochondrial integrity. Inhibiting cluster of differentiation 38 can significantly increase nicotinamide adenine dinucleotide levels, highlighting its potential as a therapeutic target. Indoleamine 2,3-dioxygenase 1, IDO1, is overactivated in human immunodeficiency virus, driven by factors like lipopolysaccharide and tumor necrosis factor alpha. This enzyme diverts tryptophan from nicotinamide adenine dinucleotide synthesis to toxic metabolites, exacerbating mitochondrial dysfunction. In aging, IDO1 activity leads to mitochondrial fission and increased reactive oxygen species, shortening lifespan. Human immunodeficiency virus amplifies these detrimental effects. Two hypotheses explain the CD38, indoleamine 2,3-dioxygenase 1, nicotinamide adenine dinucleotide depletion axis in human immunodeficiency virus-associated neurocognitive disorder. Metabolically, CD38 overactivation depletes nicotinamide adenine dinucleotide, accelerating indoleamine 2,3-dioxygenase 1 and producing toxic metabolites. Immunologically, CD38 triggers immune activation, increasing cytokines like tumor necrosis factor alpha, which activate indoleamine 2,3-dioxygenase 1. This crosstalk with regulatory T cells perpetuates inflammation and mitochondrial damage, driving human immunodeficiency virus-associated neurocognitive disorder and aging in people living with human immunodeficiency virus. Even with antiretroviral therapy, people living with HIV show elevated inflammatory markers like C-reactive protein and tumor necrosis factor alpha. This inflammaging leads to HIV-associated mitochondrial dysfunction through oxidative stress, impaired mitophagy, and direct oxidative phosphorylation inhibition. Nuclear factor kappa light chain enhancer of activated B cells pathway activation and immune exhaustion further disrupt mitochondrial function, exacerbating the condition. The interconnected web of senescence, chronic inflammation, immune activation, and mitochondrial dysfunction forms a self-reinforcing disease process. These elements are deeply intertwined, contributing to accelerated aging in people living with HIV on antiretroviral therapy. While antiretroviral therapy controls HIV replication, it only partially addresses the metabolic and immunological abnormalities driving this syndrome. People living with HIV face age-related diseases prematurely, necessitating a geroscience-guided approach. Key targets include nicotinamide adenine dinucleotide restoration via nicotinamide mononucleotide and nicotinamide riboside, cluster of differentiation 38 inhibition to reduce inflammation, and non-pharmacological interventions like diet and exercise. Senolytics and mitophagy enhancers aim to clear senescent cells and defective mitochondria, improving cellular bioenergetics. Human immunodeficiency virus-associated multimorbidity is a key hallmark of aging in people living with human immunodeficiency virus, linking accelerated aging and immune senescence. This review outlines a framework targeting cluster of differentiation 38, nicotinamide adenine dinucleotide depletion, and the kynurenine pathway. Future directions include small community trials and large randomized controlled trials to enhance health span and quality of life, not just lifespan, for people living with human immunodeficiency virus.